Hi, welcome back to our machine learning course. I'm Joaquin van Schoven, and today we'll talk about neural networks. The neural networks, as you may know, are networks that consist of different layers. Each of them have different nodes, and these nodes have connections between them. Something like this. And some outputs. Now, first of all, we'll talk about which are all these components. Then we'll talk about how we can go from some input X to some output Y using efficient tensor operations. And then we'll talk how to update all the little weights that are stored in these connections during a backwards pass with an algorithm called backpropagation. Next, we'll talk about how to design a neural network. We'll look first of all at activation functions, which are functions which are used inside the neurons to translate some input to some output. We'll talk about weight initialization, or how we can initialize the weights of these connections in the network so it can learn faster. And we'll talk about different optimization techniques we can use to update all these weights. Next, we'll look at how to implement neural networks in practice using modern libraries. And we'll talk about model selection, or how we can, through experimentation, build optimal neural networks. And we'll talk about different techniques you can use for that, such as early stopping, which means we stop training earlier before the network starts overfitting. We'll talk about how many nodes and layers we need in terms of the capacity of the network and some other concepts, such as information bottleneck. We'll talk about how to regularize the network if it overfits using L1 L2 regularization or weight decay in the context of neural networks. And another algorithm called dropout for doing the same. And then finally, we'll talk about batch normalization, which is a technique to be able to train deeper neural networks. Now, first, let's revisit an algorithm that we've seen quite a while ago, a linear model called logistic regression. So the idea there was that we take some inputs X, we then weight them with some coefficients W, we add a bias, and then we sum that up and we push that through a sigmoid function, which will then transform the output of this sum into a value between 0 and 1, so we get a probability. Right? So that was the whole model that we built. Right? If you write it completely, it looks like this. So every feature gets a value x1, x2, x2 to xp. Every feature is weighted with a coefficient. We sum them up, we add a bias to that, and that's our linear model. And then to get a prediction between 0 and 1, we push that through a sigmoid function. Right? It basically transforms minus infinity to plus infinity to 0, 1. Right? Now, if we can write this a little bit differently, like this. So here we have our inputs, x1 to x4. And we have an extra input 1, which is our bias. And these are all connected to a node or a neuron. And each of these connections is weighted with a weight. So what the neuron does is it sums up all the weighted inputs. Right? So imagine that some activation enters these nodes. In terms of our data, this means that we put in the values of each feature for each instance in our dataset. Right? So every example is given one by one to the network. Every value in our input instance is then weighted, and then we sum that up, right? Or we take the dot product, which is the same thing here. Okay. After we do that, so we take the dot product of our inputs X and our weights, and we add a bias as well, which is the same as taking the sum of all the inputs from 0 to P, and from I0, I, xi. Okay. Then this is Z, right? So Z is basically the sum of all the inputs. Right? The dot product plus the bias. And then we take Z and we push Z through, in this case, a sigmoid function. Right? Now we'll see sigmoid is a reasonable choice, but in practice we'll use different activation functions. We call this activation function. We use different functions because they tend to work better if we have multiple of these nodes working together. Right. And so at the end we get some predictions, y. We define a loss function over operated y and the actual y. And then this loss function can, for instance, be log loss. It's usually log loss when we talk about classification in neural networks. And then we use gradient descent, or more specifically stochastic gradient descent, to then update all these weights w. Okay. So this is basically one building block of a neural net. If you want to build a more complex neural net, we'll stack them together in layers. Right. Now, first of all, next to our input and our output, we now add another hidden layer h. And this hidden layer has k, in this case 3 hidden nodes. These nodes, you can call them nodes, or you can call them units, or you can call them cells, or you can call them neurons, depending on what you read. The vocabulary changes a bit, but most often they're called nodes or cells or units sometimes. Every one of these neurons is basically a tiny function, right? It takes the weighted sum of the inputs plus a bias and then pushes that through an activation function f. Right? So if you would write that in more detail, you will split this node up so that all the weighted inputs, the sum of those, or the dot product of those, is the value z. That value z is then pushed through activation function f that yields an activation a, and this activation is then the input for the next layer. In this case, you only have one hidden layer, which means that all these activations here are pushed to the output node, which again takes the dot product, adds a bias, and then pushes that through another activation function g, and this yields the output y. Okay. Important is that this activation function f or g is nonlinear. If this will be linear, if f will be linear or g will be linear, then no matter how complex your neural net, it will only be able to learn linear models. Right? So the activation function is what makes the neural network nonlinear. Right? And so all these weights, so depending on how many input and output nodes you have, there will be different numbers of weights. And overall, we can represent all these weights as a weight matrix W, which is basically for every value like Wij means is the weight for the ith input and the jth output. Right? So all of these connections together, they form a matrix, and we keep a matrix of all the weights of all these connections. And every layer has one of these weight matrices. In this case, it's only 2D because you have one output node, but it doesn't have to be. You can also have many output nodes. So this will always be, in general, always be a matrix. Okay, so functionally, we look at our inputs x. We weight them by the weights of the first layer. We add the bias of the first layer. We push that through our activation function f, which yields our activations a, right? Or the output of layer h. Then we take the activations a, we weight them by the weight matrix of the second layer. This is again a dot product, plus the bias of the second layer. We push that through our activation function g, and that gives us the output. Right? Now, in case you have multiple of these layers, this will just repeat. Right? So it kind of will be wrapped inside each other all the time. So typically we'll have many more layers. You can see here. So in the simplest case, we have only one layer, and we can then still choose a number of nodes. And of course, the number of nodes will have an effect on the number of weights we need to learn. Right? So if you have a large output layer, will have many, many, many weights to learn. Right? Now, in this figure, I'm not drawing the biases, but remember that they are there. Right? So in this case, we'll have, let's take 10 here. We'll have 100 weights because every one of these 10 is connected with 5 of these nodes and 5 of these nodes. So together, this will be 100 connections or 100 weights. And we'll also have 15 biases. That's one bias for every of these 10 nodes here, and one for every of these 5 output nodes here. Okay. We can then also add more layers, and this will look like this. So everyone is connected. So this is what we call a dense layer, or a fully connected network, which means that every node is connected to every other node in the next layer. Right? This is called a fully connected neural net. They're typically the most flexible. They're not always easiest to train. Right? In the future, we'll see specific types of layers for specific tasks which are more efficient to train than these fully connected layers. And so you can add as many layers as you want. Of course, every time we add more layers, there will be more weights to train. So yeah, if you take, for instance, 6 layers, we'll have 600 weights to train plus 65 biases. So that means a lot of coefficients that we need to train. So we'll need a lot of data to actually train all these weights correctly. And it gets trickier and trickier the more layers you have, right? Specifically because once you push data to the network, you have some outputs. You will compute loss on that, and then you have to back propagate that loss back to the network. And the more layers you have, the more that signal will get lost in the layers, and it will get increasingly hard to train. And so it's not a silver bullet. The more layers you have, the more flexible your network becomes, but also the harder it becomes to train it. Okay. Yep. Now, why do we construct layers? The simple reason is that, well, in principle, you could have just one layer and just make it very, very large, right? And this will allow us to also have many parameters and also learn very complex functions. There's nothing against this. The problem is that this tends to be quite difficult in experience. We know that you could build like a gigantic hidden layer. But it's much harder to train than having more smaller layers. And the reason for that, something called compositionality, it means that we can decompose a hard problem into simpler subproblems. And these layers effectively will act as a filter of our input data X. Right? So imagine that we have here this image of sloppily written number 4. After we push that to the first layer will transform that data in some way, like this fuzzy 4 here. The next layer will again represent it a bit differently, every time filtering the data. And the upshot of that is that since each layer learns one specific simpler filtering or simpler representation, the sum of this becomes much easier to learn than if you would have to do this in one go. Right? That's basically the real reason why we have multiple layers, to break down a very complex problem into smaller subproblems. So every layer only has to learn one specific transformation. It's not always super clear what the transformation is, but it generally makes it easier to learn if you can do it over multiple steps. Now in this case, you will see that our inputs, this input image 4, does not get filtered into one output 4 after layer 1, but this layer will construct multiple outputs. Right? And this is possible because our weight matrix doesn't have to be a matrix, it can also be a tensor. So say that we have our input X, and our weight matrix W can be a matrix, and then we'll get again one output image X accent, for instance. But instead of having like one matrix, we can have basically a tensor or a dimensional array. So we could have multiple sets of weights as many as you want basically in these layers, which means that this input x will also be transformed into a number of other output x, and these are then all passed as a tensor to the next layer. Right? This is what you see here. So our input, the image of the 4 here, gets transformed into four-dimensional images, basically. So every image, in this case, gets 4 other representations, and these are then fed forward to the network. The number of what we call filters, or the number of activations here, that's totally up to you. You decide how many of these are built. You typically also can change that, so you can have many filters in the beginning and then fewer and fewer filters in the later layers. So when we talk about images, there's a whole other literature around that, which we'll cover in the next lecture. But do keep in mind that this filtering through these layers doesn't have to be one-to-one. It can be one-to-many or many-to-one, or sometimes you can even transform an image, or you can transform this to like a 1 pixel, but then being very high dimensional, or it can have like thousands of. It can be like a 1 by 1 pixel, but having 1,000 variants of that. Okay. Yeah, so that's the basic idea. So from this raw input image here, we learn some sub-concepts, such as like diagonal lines here, or we can see some endpoints, like we see these endpoints in the figure. This one just learns like a more fuzzy representation, where we can detect the edges more easily, and the next layer can look at those edges again. And the combination of all these steps basically breaks down the problem into simpler subproblems. And so that means that over the layers, certain neurons get associated with certain patterns occurring in the data. So if you have, for instance, this number 4, it will learn stuff like having like diagonals and horizontal lines and endpoints in certain parts of the image and connections between them. And in the next layer, we'll learn like certain combinations of that. And the next layer will learn, for instance, more complex combinations of that. And every neuron basically here will activate whenever it sees in the data some combination of patterns or in the data. And the next layer, this will activate if it sees some other patterns. And then as you go through the layers, the final layer hopefully will then fire according to specific things that you want to learn. And again, we don't define what is detected. We don't define this beforehand. We do guide it a little bit in how we design the filters in this case. But overall, we don't pre-specify what to look at. The network has to learn by itself what to look at, what's important to classify an input to an output. Basic message here is that the filtering breaks down a problem into subproblems, so it becomes easier to learn. And every layer basically becomes a transformation, filtering of the input data. Now, next to dense neural networks, there are many other types of networks that we will discuss in due time. So far we've seen the deep or the feed-forward neural networks, which are fully connected. And the next lecture we'll talk about convolutional neural nets, which have a special neuron which does a convolution. We'll talk about that in the next lecture. There's a special neuron specifically for images or continuous data, such as like sound or even text sometimes you can use as well. And this basically transforms our input image to some other abstract representation of the data, and then we pass that through a few dense layers so we can match that to some output y. Right? So that this pink part here will basically extract patterns from the image, and then the second part translates those patterns into some output y. Whenever your data is like a time series, or it can be speech or something else that returns, we can use recurrent neural networks, which are networks which don't only have connections to the next layer, but they also have connections to themselves, which means that they have an extra input, which is basically their output some time ago. Right? It's like a short memory of what it outputted before. So it keeps in mind what it has seen before. So if you have a time series, the neuron does not look only at what it sees now, but it has some sort of memory about the steps it saw before that. And then there's other kinds of networks as well. We have autoencoders where we have some complex input X, like an image, and then we try to represent that in as few nodes as possible. And then at the end, we have an output again, and we try to learn the weights so that this original image gets mapped to almost the same image at the end. But going through this low-dimensional representation. And you can use that to do all kinds of things. For instance, to learn the distribution of the data, so you can also generate new examples of that kind of data. We have variational autoencoders. These have a very special kind of node, which is probabilistic. We also have deep residual networks, and these are special because they have skip connections. So they don't only connect to the next layer, but they also have these connections that skip across layers. And this can be helpful to keep in mind some patterns that are the data, but that may get lost to the layers, right? So if we saw this image 4 here and we detect some patterns, if you go very abstract, some of these patterns may get lost. And so to not lose them, we feed them back, and we skip over a number of layers to feed them back so they don't get forgotten. And this allows us basically to build deeper neural networks. I won't go into all of these. We'll mostly focus today on the feed-forward neural networks, the dense neural networks. Next lecture we'll look at convolutional neural networks.